Yeah, welcome back from me. And thank you, Arne, for the kind introduction. My name is Maximilian Luczak, and I'm an application engineer at M2M's consulting and projects team. And I'm very happy to have the opportunity to give you a short introduction to GeoDict's abilities to generate 3D statistical digital twins out of 2D input data. The import of structures into GeoDict often relies on 3D image data from microCT or FIB-SEM scans and enabling users to analyze their samples and generating digital twins and siblings. So here we see a typical workflow where you would have import, analyzation, modeling, and then designing of new structures. The ability to generate statistical twins using 2D data is, of course, highly attractive, because it's just way more available, cheaper. And so far, experienced users were or are able to deduce the structural features and create the digital twins by hand if you only got a 2D structure to begin with. For automatized usage, we remodeled our GeoApp to also work with 2D data sets. The GeoApp is called Generate Granular Statistical Digital Twins. And you can see here that you can easily pick now to choose the 2D data sets. And you can find this in the tab GeoApp or in GrainGeo GeoApps. The GUI guides you through the entire process that you need to comply with in order to use this GeoApp. It will demand from you kind of an initial guess that is needed for the structure generation. But the optimization and the generation of the 3D structures and the comparison with the information that you receive from the 2D data set runs completely automatic. But now you may ask yourself, what can you really model with grains? And I have a couple of examples for you, and maybe we can find a structure that you are familiar with. So first of all, here we see the app in usage. We have here a sphere pack, and it's a 2D image that we took out of a 3D scan. We optimized the digital twin coming only from the 2D image data and created the 3D statistical digital twin. You can see also the comparison that was made between the reference and the digital twin. So pore size distribution and so on. You can see the error that is created, but the script itself will optimize the twin to fit as closely as possible to the reference. Since we had a 3D scan where we took this from, we could also, for example, take a 3D digital twin validation, in this case, the permeability of both the reference and the digital twin, and they fit very nicely together. So here's an example of the SOFC cathode, which you have already seen this morning. It's the same principle. In this case, we only have a 2D SEM image, but we were able to use this with the app and create a digital twin, which you can see on the right-hand side. Here is a sandstone thin section, also from a 2D image. You create the digital twin, and you can also predict then, of course, 3D properties like the permeability of this digital twin and have this information available to you. Here we have a NMC cathode from a lithium-ion battery, a conventional one, again taken from a 3D FIB-SEM scan. We used it in the 2D to 3D GeoApp and referenced here the tortuosity of the 3D original scan and the digital twin to validate the results. This is a Titan mesh. Again, 2D image goes into the app. We create the digital twin, and you can see that we match it quite closely in this case. This is an anode from a lithium-ion battery. Again, taken from a 3D scan, and also tortuosity between the reference and the digital twin can be seen here. This is the last one that I want to show you from the example list. This is a fuel cell catalyst layer. It's quite a difficult structure, so to say, and we can see that the pore size distribution in this model is not yet sufficient, but we need more validation examples to make this work better. But this was like a short overview of all the different applications that you can tackle with this 2D to 3D structure generation GeoApp. And in order to gain a more detailed understanding of the math behind all of this, of 2D to 3D structure generation, I'm very happy to introduce you to Dr. Orkun Furat from Ulm University's Institute for Stochastics, who will give us a presentation on the latest advancements in the academic world. And please welcome Orkun Furat.
Thank you, Max. So yes, and thank you for welcoming me here. I'm happy to present our latest results within a project called Delphin. It is on digital electrode design for all solid-state batteries, together with Mark to Market and the company RDL Micro and Analytics, as well as the Justus Liebig University of Gießen. Yes, and as Max mentioned, I'm from Ulm University. All right. So, and the focus of my talk will be on models that can generate virtual microstructures that have various applications. The focus will be on all solid-state batteries, so ASSB cathode microstructures, as well as reconstruction from 2D to 3D. So using 2D data to calibrate 3D models. We heard the advantages of it earlier already. So I will start with a motivation, and afterwards I will talk about two different types of cathode microstructure models. One is using generative adversarial networks, or GANs, and the other is by using excursion sets of random field models. So some of them, so these excursion sets you've already seen in Max talk already, so they are also implemented in GeoDict. Then I will talk about some three further applications where we reconstruct 3D microstructures statistically from 2D data. I will start with so-called heteroaggregates, which we observe in so-called STEM data. These are projectional images. Then the microstructure of SOFCs in anodes from 2D SEM data, and in the end for polycrystalline materials occurring in cathodes of lithium-ion batteries using 2D EBSD data. But more on that later. So first of all, motivation. We've heard about this already. So when we have image data here on the top left, how do we quantify the microstructure? So the most important thing, and it is a bottleneck in many cases, but this won't be the focus of this talk, is the image segmentation. So identifying, for example, individual objects. After you've identified individual objects, you can statistically describe them or stochastically describe them. So on the bottom left, we see a multivariate distribution of two descriptors of these objects we see here. So on the x-axis, there's a diameter. On the y-axis, shape descriptor, the sphericity, so describing how spherical the object is. And here in these yellow areas, you see descriptor vectors that occur with a higher frequency. So this is one way to describe materials that you observe in image data. Another is via stochastic geometry models, or we sometimes call them stochastic 3D models. So now I will show you why this can be an advantage. Because the problem is that descriptor vectors can be ambiguous. So here we see two objects that have the same area and the same parameter. So in 3D, this would translate to the same volume and the same surface area. And when we characterize materials with probability distributions of descriptor vectors, this ambiguity transfers to that. So here we have this 2D distribution. We could simulate from that and get a random vector. And then it is unclear how the actual particle or the actual object looks like. So there's some ambiguity. Stochastic 3D models or geometry models can avoid this issue. They also describe a distribution, but when you simulate from this distribution, you obtain a random object, a random morphology, geometry, and from that you can derive anything you want. So, for example, these descriptor vectors and then the joint distribution of these descriptor vectors. So you can see that in this chain of information, 3D models are way more informative. And now to one possible application of this. So Andreas pointed this out in his talk already, this triangle. So this is, in this slide, I want to refer to two parts of this triangle. Structure influences macroscopic properties. And yeah, in many cases, the influence of the microstructure on material properties is investigated. And one sort of conventional workflow is producing numerous materials, doing 3D imaging, microscopy, image processing, and you derive microstructure characteristics or descriptors. And you can also use these synthesized materials to do experiments, such that you can obtain the macroscopic properties, but you can also do numerical simulations to simulate the properties. And then when you here on the bottom left and the bottom right, you can investigate structure-property relationships to understand how the microstructure influences our materials. However, to do this, you need a broad database. So you have to manufacture loads of different microstructures and so on, materials with different microstructures. And so there's a huge experimental workload, and you can avoid a little bit of this, or a substantial part sometimes also of this, by using stochastic 3D modeling. So by having parametric models with interpretable parameters, which you can calibrate to data to have digital twins of the microstructures. But you can also investigate with the parameters new structural scenarios that were not manufactured yet, that are still realistic. And with the synthesized, with these digital twins, these stochastic 3D models, you can go both routes. So the image analysis to describe the structure and do the numerical simulations to derive macroscopic properties. And with that, you can broaden the database for investigating structure-property relationships. And now to my main part of the talk on all solid state battery cathodes. So here we can see some electron microscopy image on the left-hand side that has been segmented into 3 different phases. So the black part is some remaining porosity. The active material is here in gray, and the beige part is the solid electrolyte. So here we had 2D image data available, and I will first focus on the 2D part, how we analyze it, how we calibrate the model on it. The 3D part will immediately drop off because we assume here isotropy, and the model can be instantaneously simulated in 3D. So first of all, another approach that was recently developed for microstructure modeling. So this goes towards generative AI, namely GANs. So there are these approaches for doing 2D to 3D reconstruction using generative adversarial networks. So when you have only here on the left-hand side 2D training data, you can take some small patches here marked in orange, and the generative adversary network here on the right-hand side would receive Z as noise. This would mean noise as input, and its task is to transform the noise with some function G to generate realistic microstructures. G is here a neural network, a convolutional neural network. And how do you calibrate, or how do you train the weights of these networks? Basically, you simulate measurements. You generate a virtual 3D image, then take virtual cross sections from that, so you get to these blue patches or the blue bounded patches, so that you have virtually simulated measurements, and on the left-hand side you have cutouts of measurements, and these are passed to a neural network called discriminator, and its sole task is to distinguish between these 2 types of images. But the generator, so this neural network here denoted by G, gets feedback of the discriminator's decision, and it tries to get better to fool this discriminator. And with that, you train a model that can generate virtual 3D structures that has statistically similar 2D sections. So in this case, you can use 2D image data to train a 3D model, to generate virtual 3D microstructures from 2D data. The disadvantage of this approach is that this generative model G is highly parametric. So it has so many parameters that are uninterpretable. So this virtual materials testing, which I showed in the beginnings, where you use stochastic 3D modeling to investigate new structural scenarios, becomes difficult because you can't tune the parameters of the neural network so easily. So it is easy to calibrate a model that can capture statistics of data, but to investigate new structural scenarios becomes more and more difficult with these models. And here is another, our solution for this is using a stochastic geometry model. So we want here also to use this framework of generative AI. Here we go back to our solid state batteries. So on the top, you see random cutouts taken from the experimentally measured data. And here on the bottom, we want to generate virtual samples that look statistically similar. So obviously this on the bottom doesn't look statistically similar, so the model has to be tuned. And we want here to substitute the neural network part G with an interpretable model, but calibrated with the techniques from generative adversarial networks. And now for the model part. So for that, we used so-called excursion sets of random fields. So let's start with random fields. I visualize them only in 2D, but they can be also similarly modeled and described and simulated in 3D. So random field is basically a function, a random function. So here on the left-hand side, you see a realization of a 2D random field. So you have spatial coordinates, and at each spatial coordinate, you have a random value. Obviously, these random values are correlated. Otherwise, you would just see noise on the left-hand side. So there's some spatial correlation. And an excursion set is then achieved by just thresholding this random function. And with that, you immediately have a model for two-phased materials. So here in black and white. This is a stochastic model with which you can generate two-phased materials. And then you can go on and make also a model for three-phased materials, because that is our data scenario for these ASSB cathodes, where we had active material, solid electrolyte, and remaining pores. So basically, we would require an additional random field, which you then threshold, and then basically fill up this black area with the second phase. The third phase would be then the complement of the first two ones. And now I want to tell you a bit more about the model we use. It's a bit more complex, but it can capture various types of microstructures. The technical details I will refer to you. Sabrina, my colleague. She's over there, and she has a poster on that, which you can look at later. So our model has some interpretable parameters. So for example, some parameters that define kernels. So here on the right-hand side, you can see such a kernel. These kernels can be used to define Gaussian random fields. What's a Gaussian random field? It is one where each random value of the function follows the Gaussian law. And you can simulate this by just taking noise and convolving it with your kernel. So here are two different realizations of two different random fields that have a different underlying kernel. On the left-hand side, you have this random field with broader structures, and on the right-hand side, one that has this finer structure, which would imply, for example, smaller, faster decrease of correlation when you look at distant points. And with that, you can simulate random fields. You can do lots more with them. So you can do linear combinations of random fields to have correlated random fields. That with that you can model, for example, repulsion or repulsion effects or attraction effects. So if one material attaches itself to another, this can all be modeled with those. But the technical details for that you can look at Sabrina's poster. So in the end, when you have two random fields simulated here, we can do the threshold of the first one, with which we can get the first phase. So in this case, this would be the solid electrolyte. Then we have here a realization called Y of the second random field, and there we take the complement of the first phase and threshold it with respect to y, and with that we get the active material phase. And here on the bottom right, this would be the remaining phase. And we plug this into the generative adversarial network framework. So instead of G being a neural network, which has millions or billions of parameters that are uninterpretable, we plugged in our stochastic geometry model and calibrated it using these GAN techniques. So it produces then 2D images that are statistically similar. So here on the left-hand side, you see a 2D image taken from the microscopy images, and on the right-hand side, simulated data. And as the model is isotropic, it can immediately be simulated in 3D. We can later introduce some anisotropy if we want. So if we have data on that can be later on introduced. But this model can be immediately simulated also in 3D. So we calibrated this only with 2D data. And here are some structural descriptors of the realized of the generated microstructure. So we have here volume fraction, arid chord length, and specific surface areas of the different phases within the material. And overall, it looks quite good. So small errors, but except for the specific surface area for one phase, we're still looking into the issue there. But otherwise, with respect to various descriptors, this method performed quite well. Now to some other application where we have some completely different geometries and where we used stochastic geometry models and neural networks for using 2D data to calibrate our 3D model. So here we had a model for these heteroaggregates. So these are aggregates consisting of two different types of particles, here just marked in red and green colors. And here we have this, okay, this pointer is not working, unfortunately. We have a model that can generate random heteroaggregates, and it is controlled by this parameter called theta. And we generated numerous 3D aggregates and put them into a STEM simulator. So this is imaging technique that provides projectional image data. So it's an integration through the material. And with that, we had virtual training data. So the training data comprised of the simulated STEM images, so the projective images, and our model parameters that describe the entire structure of the aggregates. So how compact they are, what are the volume fractions of the different materials, the size of the aggregates, and so on. This is all covered in these model parameters. And we trained with that a neural network. It received the simulated STEM images as input, and the output were the model parameters. They could be plugged into the model, and then we could generate arbitrarily many 3D aggregates. And here, this is on the bottom left side, which we could then statistically compare with the actual 3D aggregates. So this is one example. Here is another example, which has basically the same workflow, but completely different morphology and also a different measurement technique. So for more details on that, my colleague Leon Schröder here has also a poster on this work. This is basically a similar model as the cathode model, which I showed before. And this has been calibrated using scanning electron microscopy data that we have simulated. So we simulated virtual training data and then trained a neural network that could take 2D images as input to predict our model parameters. And with that, we had the full 3D information. And my last example is on polycrystalline materials. So here we had 2D image data of the polycrystalline microstructure in NMC cathode particles. And here you can see individual crystals colored in individual colors of this particle. And we only had this information in 2D. First of all, we represented this pixelized polycrystalline microstructure with a low parametric model, geometry model called a tessellation model. And with that, you have a huge reduction of complexity. Basically, with that, you can tessellate space or define these mosaics by point patterns. And with that, you have you can model them these microstructures more easily because you only have to model the point pattern instead of the individual pixel values. And here we also used generative adversarial networks to train the point pattern distribution using 2D image data. With that, we could generate virtual 3D microstructures. So overall, these AI techniques, just to sum up quickly, they can cover many different morphologies with similar techniques and different measurement techniques also. So projective images, 2D cross-sections, or top-down views. So, the last announcement would be that the ASSB cathode model will be implemented in GeoDict 2025 and will be released. Yeah, I don't have a date on that, but yeah, the plan is to release it in the GeoDict 2025 version. So thank you for your attention.